What's up, guys? Long time no see. We're a paper channel, latest archive works, applications, the speech, language process, large language. Today, we're gonna be reviewing a paper published back in 2023, Bowen by Meta. Everybody call that VoiceBox. They named themselves most versatile AI for speech. Basically, it be able to complete the following tasks. First, in context TTS, also editing the speech and voice reduction, and also cross-lingual style transfer. For example, I'm Spanish, if I sound, I speak Spanish. Also, the diverse speech sampling make the speech more representative. But people may wonder what type of technology are they using, what the data they are using, why they're so advanced. Today we're going to be reviewing the paper. It's the VoiceBox text-guided multilingual universal speech generation at scale. It's by Matthew Lei, Apoorv, Vyas, Bowen, and Brian Carrier. Other authors from Meta. And of course, the paper mentioned that the accessibleness of GPT-based method, generative method, DALL-E, diffusion methods, and they are talking about talk about the methods, not the methods. Task. First, let's see the denoising. Bigger number have raw data supposed to try to get rid of those noise in this menu. This is better. And also, suppose you put a style here. They're saying that text prompt with this, then you're supposed to get some. They also get something like only sample, and you can see more like a mask, different synthesize the voice. I would say that it's fairly powerful because all of this just coming from one model. I think in the past, we may have to develop the 3 models with. They also covered something about the related works. I'm not gonna cover it today, but definitely I think I have read the paper VALL-E. Check. I have a paper reading. And when they're talking about the method, they're using flow matching with an optimal transport path. Flow matching is not new. Check paper published this year, about 4 months before they published the VoiceBox. It's also Meta AI people. There is a paper called flow matching for generative model, but this thing was being applied on image. They talk about flow matching, but I do want to quickly go over the very first paper that leads all to this, which is This is the paper published in 2019 or maybe earlier, 2018. Yips. This is the neural ordinary differential equation. I will first start from here, okay? This is the basic idea. I won't go into line by line paper. First is, let's see the figure 1. Suppose you have a residual network shown in equation 1, then you can get the flow. You can see each of the arrow, the length of each arrow means the norm of the derivative or the gradient, and the direction of the arrow means vector, the vector points or what the thing flows to. And you can see on the residual network, basically, you can see this is a layered ID, right? 5 layers and the input, right? And then you can see on each layer, you can compute those gradients, but these are being done in a discretized system. But once you add more layers and take a smaller step, like the author mentioned, and in a limit, they can go from the equation 1 to equation 2. And this is, I think everybody learned the calculus, right? This is the ODE, ordinary different equation. And interesting thing is, the function here is actually a neural network. What does that mean? If you take a look at the picture on the right, you can have not just the gradients at the time I or time 1 or 2 or 3 or 4 or 5. You can have any time. This is you see that. Look at this time. It's not on the 1, right? This is probably on the 1. This is greater than 1, not 2. You can have all of these and all of these gradients. And what makes that thing more interesting is once you get, I think I shouldn't call that gradient because this is no longer the traditional stuff. Derivative or partial derivative. This case is derivative, right? Once you get a derivative, you can definitely use the Euler's method. Euler's method is just, suppose you have a time t0 equals to 0, and then what's the function's value at the, and then you take one step forward using the derivative you get and add on to the initial value of the function. That you keep doing this until you reach to the t equals to capital T. Okay, this is very standard way. And what's the benefit of this is that you do not have to save anything in the memory. This is called ODE solve. Because later on, I think I will speed up a little bit. Later on, suppose you want to calculate the gradients. So suppose you want to go back propagation. So you want to get the gradients of certain update your neural network. This is the equation they will go with to detail. Their appendix is very clear about how they come up with these equations. This is okay. This is the conclusion you have to. After you initialize everything, then you use the ODE solver, so you can get the partial derivative of the loss with regard to z of t0. And what is more important is this. This is, I think, is to me is more important because then you know how to update your parameters, right? Theta is your parameter. This is, and what's different from the traditional backpropagation algorithm? The difference is that you no longer have to have a cache in the memory to store the intermediate variables when you do the feed-forward operations. So the memory complexity right now is 0.1, but traditional neural network model, I think there is a big table here. You see, in the traditional or MLP or neural network, I think your memory cost is OL memory, but this one is OL, 0.1. Very appealing, very enticing. This is why these authors are exploring this. And by using this, you can stuff more layers into one GPU because the memory of the GPU is limited. You want to have more layers, then you have more GPUs, but you have a limited amount of GPUs. You have to use simpler method of the gradient calculation. Okay, and then check the flow matching thing. Then you have to know something called normalizing flow. So why did they come up with the normalizing flow? It's always, well, imagine this. You have a normalized distribution, okay? Let's call that 0. And then you want to apply a transformation or operator on this distribution. So you get another distribution. Let's call that Z. A random variable. So this is a PDF. This is go from Z0 to Z1. And then you keep doing this until you reach to what? You goes to from this and you reach to a distribution of letter O. Probably have another way more sophisticated distribution. And then if you have check our channel, this might sound familiar to you or look familiar, because this is basically the cascaded diffusion model. Exactly. And then normalizing flow is also cascaded diffusion. But the only thing different from that, or the only thing special, is that there's a nice, so I think, word for that. I think it's better to open a website and read that to you. Okay, they're saying that normalizing flows are a method for constructing complex distribution by transforming a probability density through a series of invertible mappings. What does the invertible mapping mean? That means suppose you have this function, and there is the function is reversible, so that this can go back to 0. You all know what is invertible function. This is a nice feature because, and then the author omit one thing, which is this equation, before getting this equation, because they have to go from log p0 p0 p0. This is actually plus log det, determinant of partial derivative of invertible function value with regard to d1, and this is inside of the. But because the inverse, because they are limiting the function or the converting function in as this specialized invertible function, so this function has this nice feature. So this can be deducted using, I think you have to check the matrix operation. I won't go into details today. And get this. And then what's the nice feature of this? Suppose you want to get, like here, so all we have talked about is not continuous normal flow. Right now, we only come up to normalizing flow. And you keep doing this, you can see you go from Z0 to Z1, then Z1 to Z2, blah, 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 until you got to ZK, I think. And then, okay, what's next? Because the author come up, Chen and his colleague, they come up with this ODE network, so they can go from the discretized ODE into this type of a continuous network or something. Sorry, I didn't have the right terminology for this, but you get what I'm saying. They can compute continuously compute the gradient. So they are not computing the gradients or the derivatives on integers, right? On those integers. They have every time. Once you have the gradients of every time, you don't then you can go from here to this. What is this? Because you go from this discretized representation to continuous representation. So then you have, let me change another color. Then you have the continuous normalized flow. And then once you go that way, when you want to compute the log p of z of t with the partial derivative with regard to t, and then you take the derivative of the log of determinant of the function's value, the partial derivative of the function value with regard to z dt, okay? And this has a nice feature. This is the trace. TR means trace of the function. So you no longer have to compute the determinant of a matrix. You get me? Let me go a little bit further. This one is actually a Jacobian matrix. If you don't know what I'm talking, check the keywords I'm talking about. Go and search on the GPT-4. And calculating the determinant of Jacobian matrix or matrix is very costly because it's not it's not necessarily a diagonal matrix, right? But calculating the trace of a Jacobian matrix is very simple. How do you do that? I will leave this as a homework. It's very fast, very efficient. I think right now you understand why the author wants, or why these researchers are using a normalizing flow in which the conversion function are all invertible functions. Okay. I think now let's come back to the methods. Okay. I think you understand what is neural ODE and also what is a continuous normalizing function. Then the author in the voice box mentioned that the flow matching. So I do have to close this by checking, give you a quick overview of what the flow matching is. Okay, you look at the flow matching paper published in February 2023, also by Meta people, and then this is the flow matching objective. If this is not that obvious to you, let me go over it. So VT of X is the generation process. Okay. Say you have a normalized function, then of course this time is no longer discretized, right? This can be any t. This is 0 and this time eventually come. Then VT of X is given this random variable distribution. You sample one from V0, and then you go to VT of X. You just go through this flow of generation. And once you generate this, you want to ask what my VT of X should be. The answer is that you check what the UT of X should be. UT of X is the reverse I think they have the word for that. Reversible. Reversible, right? The word is reversible. Change the color of the thing. So once doing the training set, you have a letter O's instance, right? So you go from that one to the K, from to anything less than K, right? Doing this until you reach to the original or the initial T0, at the time which the U of 0 should be a normal distribution. Get it? You're from complex to simplified distribution. And on this stage, you have many times, right? Because this is continuous. Then you get a distribution called the UT of X. And then you sample with the X, okay? Then you get an instance. Then you compare that instance with the generation process. See? Compare these two things. And you want to say, it's obvious, you want the norm L2 norm to be as small as possible, right? This is what's being shown in equation 5. And this is called matching, right? And also this is a flow, right? You see the backward flow and the forward flow, all flow. Then you can remember this is called flow matching method. Okay, after we explain the flow matching method, you can see that in the voice box, they are playing exactly with or almost the same thing as the flow matching method for image generation in voice box, audio and speech. See, this similar to the flow matching method equation. This is also the same, right? Same. Then they come up with, they do mention something new. yes, you already have the conditional. It's not paper, flow matching. But I will this is called conditional propagation method. The only thing different is that think about when you go from the simple complex distribution, you can generate the u sub t of x given the previous random variable addition of given previous sample, previous random variable. There's found that this is better versus non-conditional. And also the VoiceBox part, they do have something. They introduce something optimal transport conditional path, which is they introduce some standard deviation control terms. I think it doesn't the intrinsics of the method. And then I think it comes to the speech part. How do they formulate the problem? Problem is that first you have to have transcribed the speech. Okay, this is no longer supervisor learning X. X is the audio sample. Y is the transcript. And they sometimes they use the mask. This is a masking operation. And the X MIS means it's missing the missing part of the audio. Missing audio. And the XCTS means context text of audio, which is a mask. And the generative model, they learn two things. Or yeah, the first of all, they learn that suppose I give you a transcription or a prompt, which is Y, and also the existing audio you have. Can you fix the missing part of audio? So you can see this is pretty much like the audio editing. And when you just set XCTX, I think, then you get a TTS problem. And then the details is like this. They run something called a false alignment with the audio and transcription, the phoneme level, yeah, the phoneme duration. And then they come up with something or define something called Z. Z has the same size of audio X. So they literally have the frame level from. Okay. So by doing this, they were able to convert the generation problem, which is this, shown in section 3.4, to two problems. First is given Z, what is a missing X? Given Z and the context audio, what is the missing audio? And also they wanna say this has nothing to do with audio. Suppose I give you the phonemic label and also the existing or context phoneme. What are the missing phones durations? This is all about duration estimation. That's why I call duration model. This is yeah, I think they need to improve a little bit on their writing. I think it's not easy to understand. And this actually they meant M means the frame level mask, and M astrophy is the mask on the durations. So the M is for X, M astrophy is for, okay. Those are settings, and you can see this is their loss function, and you can see this is like a control variance controlled x0, and this thing, this is a backflow generated sample. Back is the first you get the distribution from the backflow, then you sampled at the backflow at the time t, then you get this, then you compare it with your feed forward or the forward flow, which is the v sub t. The v sub t is conditioned on x context audio, z, and yeah, w is also, yeah, I think this is also context conditioned on. It is the model parameter. And then they're saying that by doing this, you're just trying to make everyone happy. How do I say that? Saying that they're computing the loss on all frames, which so they added the mask. The loss function is focusing on mask read. Better. And for the duration model, is much more easy to understand. Is you want to minimize the difference between this, something you want to estimate. This is what you generated based on the focus on missing region by the mask. Inference is very straightforward. I don't think I would have any difficulty understanding that. I will just quickly go through the applications. First of all, zero-shot TTS, how do they do this? I think given a target text, it's TTS, you have to have the Y, you have the transcribed reference audio. So you have an example, I understand. And then the zero-shot TTS aim to synthesize speech resembled but only unseen audio style reference. They perform the task by treating the reference audio and the target speech one utterance. See? You can see this is reference audio. They put it here, right? And then they're saying that, okay, the target audio should be together with the reference audio, or at the beginning of the reference audio, right? To the beginning of the reference audio. And they smartly add a mask on it. They're saying that mask, but actually they do not have anything to mask. All the model has to do is to, given the reference audio and given the text including the reference text and target text, then you generate the target audio, fitting the mask. How the zero shot works in case. Next one is a transition noise removal and editing. I think that's similar to zero shot case. I could go over for you. But the denoising is that, okay, I have the audio and I have the reference, and I'm saying that, okay, maybe I can use some signal processing based method. I found that, okay, over this region the noise is too much. So they just apply a mask on it. You may ask, okay, if they mask out all the audios in this region, would that be an issue? The result turned out to be that if you remove everything from this region because it's too noisy, then you regenerate or resynthesize this part. It's not that bad. You're just taking the current model, the model, and use a model to estimate based on the transcription and the context audio. They tell what audio in the masking region is. And of course, I think the method they do look at the original audio, not just throw away the original audio. Yes, I think they didn't throw away the original audio. Have which is this adds this. Diverse speech sampling, I think, is to generate sample by infilling the whole utterance. What does that mean? So that means in this case, there's no reference audio or no context audio. There's only just reference text. So you mask everything, and you generate things with the directions given by different. Okay, so they also shown a table which they're saying that their model can do all the 4 things other people. They're showing the word error rates and others objective measures are way better. Others, those are different tasks. They're doing extremely well compared to other methods. Okay, especially when you compare to VALL-E. I personally not think that using WER is a very good, but I do think the authors should include human evaluation. Same is cross-lingual zero-shot TTS. Self-nation noise removal. Oh, this is very impressive. Very, very well. Diverse speech sampling. I think this is value with it. I think using WER may not be a good way of evaluating this. Important thing, diverse speech sampling first, and you good. Yeah, FSC. That cool. Yeah, I think the following things are. Yeah, the conclusion, I think, when they come up with this, they're trying to say that by leveraging the continuous normalizing flows, they're capable of very, very large model. Data. Remember, they have yeah, they train with 40K hours of data, and then because they use like mentioned that the use of the normalizing flow, the training speed is very fast. Permanent, traceable. It consumes less memory. That actually ODE server versus is one versus. I guess is that they can train the model very large model. Increase the model. If you're interested in how big the model is, you can that way next generation the advantage. Better data for training. Fast. That way. I can. That just subscribe our channel.